the integral as an accumulation or amount of change. Consider the integral from a to b of f prime of x dx. The interpretations we've talked about in detail are as follows. It is by its nature a summation of very small things. As written, it is the summation of very small rectangles, which leads to the interpretation of being an area under the curve from x equals a to x equals b. And then we also saw that the integral was an antiderivative. For our final interpretation, let's rewrite the integral using different notation, where f prime of x is delta f of x, or df of x, over delta x times this delta x back here. We can simplify this because those dx's will cancel, and then rewrite our integral as the integral from a to b of delta f of x. So what is this here? It is the summation of very small changes in f of x, where we can think of, if I look at x equals a and go to another x value right next to it, that area gives a very small change in f of x. And then if I do from that x to the one right next to it, this new area gives us another really small change in f of x, etc., until we get to the very, very last one. But the point of this is, if I have very small changes in f of x, the first one, the second one, etc., out to the very last one, what does that give us? Well, that gives us the total change in f of x on the interval a to b. Again, the sum of these small changes in f added all together gives us the total change in f on the entire interval. And how do we find a change in a function value? Well, it's where I end up minus where I start. So we see that our final interpretation, an accumulation or amount of change, says that the integral from a to b of f prime of x dx equals what? Well, it equals the function, not the derivative, but the function at the end point minus the function value at the start point. Quick example. What if we want to integrate 2x from, say, 1 to 3? We could certainly draw a picture, but let's do this using a more algebraic approach. We know that the antiderivative of 2x is x squared. Now, you might think we need to put a plus c. I will for this first example. And then I'm going to put bars like this. This is notation that says we're going to integrate from 1 to 3, but I know that I should find the value of this function, my antiderivative, at the endpoint. So 3 squared plus c. And then subtract the value of my antiderivative at the start point, minus 1 squared plus c, which gives us 3 squared, or 9 plus c, minus 1 minus c. Now, what happens when we have a definite integral recall that a definite integral is an integral that has limits, so I definitely know where I start and where I stop. What happens with the c's, if you do it correctly, that constant of integration will always subtract out, and we'll end up with 8. Let's do another example here. Let's integrate x squared plus x cubed on the interval from 0 to 1. What is the area under this curve on the interval from 0 to 1? Well, I can think of this as being the derivative, and to find the value, I need to find the antiderivative of each, in this case x cubed over 3 plus x to the 4th over 4, from 0 to 1. Where I know that if this is f prime of x, then this integral will give me the change not in f prime, but the change in my original function f, where this is my function f. So we're going to plug in the top value. I'm plugging f of 1, giving us 1/3 plus 1/4. We'll subtract. Now we'll plug in the starting value into x, giving us 0 plus 0. And putting these things together, we get 4/12 plus 3/12 equals 7/12. So this value, or if you want to think of it as the area under the curve of x squared plus x cubed from 0 to 1, equals 7/12. We're going to do a lot more of this in the next video, plus other examples where we use this idea. But what I've introduced in this video is something called the fundamental theorem of calculus. What I usually call part 1, just because I personally teach it first, or FTC part 1.